All right, cool. Yeah, so as my title says, I'll be talking about analyzing a particular kind of diffusion process called Langevin diffusion in some setup that has to do with having manifold structure. This is joined with Ankur, one of our organizers. I should say I don't have complex structure in my talk. I will have complicated structure. All right. Anyways, so let me start really, really high level. What's happening here? All right, so kind of to set a little bit of context, one major motivation for what I'm going to be talking about is sort of unsupervised learning in general, which is has to do with learning when you have unlabeled data. And what the heck does that mean? So there's sort of some classical things that people have done, which is trying to understand some kind of structure in your data. So this could be some sort of latent information. So maybe you want to automatically learn some causal structure of symptoms and of some diseases. Maybe you want to figure out some kind of clustering of your data. And then there's sort of more modern, I guess, on steroids applications of these things where maybe you want to learn how to sample from a complicated distribution and at that do some kind of complex conditioning. So maybe you want to, do like a nifty thingy like this where you want to move through the space of faces by sort of changing features ever so slightly. And then kind of also related things where you want to be able to extract some features automatically and sort of transfer them to something else. So maybe you want to figure out how to pull out the lines from a zebra and put them on a video of a horsey. Very useful. All right. So just to sort of, I guess, make the motivation a little bit more concrete, one very popular sort of paradigm in unsupervised learning is what's called the latent-variable paradigm. So these are instances where you want to postulate that your data is simple if you condition on some variables that you get to not observe, or latent variables. So in the sort of examples that I had on the previous picture, maybe I want to model a joint distribution of symptoms and diseases. And of course, the latent thing here would be the diseases, and the observables would be the symptoms. And I write it as a product of the probability of the diseases times the probability of the symptoms given the diseases. And I think that these two factors have some simple forms. So maybe the diseases appear with some independent probability. Maybe the symptoms also appear with some independent probability. And then one particularly common task that you might want to do is what's typically called the inference task. So what's the inference task? It's very natural. You get a new patient. They come to you with some symptoms. You want to sample what's the posterior probability, which would be the probability over the diseases given the symptoms that the patient is exhibiting. So wherein lies the rub? Why is this sort of not a simple task? So you can whip up your sort of handy Bayes rule, so you know that the probability of the diseases given the symptoms is proportional to the joint probability of the diseases and the symptoms. And we know that this has some simple kind of explicit parametric form. But of course, the problem is the normalizing constant, right? So this normalizing constant would be some complicated sum or maybe integral. So you sort of have to marginalize over all possible combinations of diseases that a patient might have. And these are the typical kinds of things that give rise to computational intractability. So let me abstract this away. The problem that we're going to look at is the following. So I want to sample from some distribution. It's parameterized as follows. So p of x is proportional to e to the minus f of x. Let's say it's all over Rd. And the way I'm going to have access to this function f is through, let's say, gradient or value queries. This clearly subsumes what I had on the previous slide, because in the previous slide I even have some explicit form for this f of x. And of course, what this should remind you of is basically the kind of prototypical black box optimization setup, where what you have is little black boxes for a function, and you can input some points x, and it spits out for you the values of the function evaluation or the gradient. Is the abstraction clear? Feel free to stop me at any point. Let me say the sort of the loss, I guess, like loss of generality here is the access method. Of course, like the fact that I'm assuming that p of x is proportional to e to the minus f of x is without loss of generality, because I can always take f of x to be just minus log of p of x. So supposing you could do this task, like what are some applications of this? Probably the most boring one, meaning that I can't show you a picture, but the most important one is diagnostics. So oftentimes what happens after you've run your training algorithm and you fit some model, what you want to check is how well does the model fit, right? So you want to evaluate the log likelihood of the model. And it turns out that you have to, like, these are exactly the kinds of, these kinds of posterior sampling tasks is exactly the type of thing that you need to evaluate. Of course, in this running setup with symptoms and diseases, maybe the sort of the way that you are using the model is exactly like, you have a patient, they come with some symptoms. I should say maybe this is not the best time for this running example, but like the slide was there beforehand. So there's like, a patient with some symptoms, you want to figure out what's the probability that they had a flu or heart attack or something like that. And the more modern versions of this can get quite crazy. So there's sort of these kind of multimodal models where what you can do is you can put in some description of a picture. So a small bird with a pink breast and crown and black primaries and secondaries, and you run it into your model, and then they can sort of, it chugs basically, and it spits out some samples that sort of look like this description. It's a little hazy, but pretty good. And if you care about these things, so there's a pretty recent paper from Stefano Armon's group in Stanford, which can basically get state-of-the-art, I guess, performance on certain measures of quality for unsupervised methods with exactly the kind of diffusion processes that I'm going to be talking about. And so I'm sort of giving you here a snapshot from their paper. I guess the thing to look at is that the picture quality is sort of much, much better than some classical things like VAEs, and sort of is getting comparable quality to GANs, which was pretty difficult for non-GAN models, like up to very recently. And I should say, depending on your particular, I guess, background, you may think like, it's like, maybe most of the time that I care to do sampling, I can actually just do optimization. Like, does it actually matter? And I mean, maybe it's clear from the previous slides, but I think it does matter, right? Like, so for instance, in this setup with the symptoms and diseases, you want to spit out some probabilities, right? Like, you want to check, it's possible that for a particular combination of symptoms, there are multiple kind of reasonably probable diseases, and you want some kind of confidence intervals, and you don't want to be wrong, because sometimes if you spit out something that's way off, so maybe somebody came to you with fever, rash, and blood pressure, you don't want to say that the probability of appendicitis is 0.9, because then you have to put the patient through an unnecessary procedure. And if you think about this kind of image generation setup, maybe you want to generate some pictures that kind of look like some description, so maybe a scientist in a lab coat, and then sort of something more subtle goes wrong, so you basically output a bunch of these sort of stock picture looking things of a white male scientist that kind of sort of looks like a scientist, right? But what the problem is that you're missing some parts of the distribution. So presumably this distribution had some portions for Indian scientists, female scientists, and these are sort of, if you deploy these things in the real life, like these kinds of, things matter for fairness considerations. Okay. So hopefully that motivates you enough. So another nice thing about this setup is that there's basically a very natural, like much in the same way that there's a natural algorithm when you're trying to do black box optimization, there's kind of a natural algorithm for doing sampling in this black box setup. And it's actually an analog of basically gradient flows, which is sort of the continuous, I guess, version of gradient descent. So what is this Langevin diffusion? So it goes as follows. I'm going to look at the limit as the step size is going to 0 of the following Markov chain. So if I'm at some point xt, what I'm going to do is first I'm going to sort of take a gradient descent step. So I'm going to move opposite of the gradient, and then I'm going to inject some Gaussian noise, which is appropriately scaled according to my step size. And if I let the limit of this go to 0, what I get as a result is what's called a stochastic differential equation. So it's basically something that says the change of your point is basically sort of a drift in the direction opposite of the gradient, and then I'm injecting some Brownian motion. If you haven't seen stochastic differential equations, don't worry about it. You can just think about the discretized version. There's nothing sort of deep that I'm going to be using about SDEs. So why is this particularly natural? Well, if I ran this process basically, as time goes to infinity, the stationary distribution, which you can think of as the equilibrium distribution that this converges to, is exactly the distribution that we're trying to sample from. So it's P of x is proportional to e to the minus f of x. And I should say one thing here, which is depending on what kind of background you come from, so when you're doing optimization, really the scale of the function doesn't matter. And this is not the case for sampling. So for instance, if I plot for you here the distribution e to the minus f of x and e to the minus f of x divided by a bunch of like numbers in increasing size, like over 10, over 50, over 100, the distribution gets flatter, and you can imagine that the flatter distributions are easier to sample from than peakier distributions. So that's something to keep in mind. Questions up to this point? Cool. So there's a kind of natural dichotomy between sort of what I guess like what classes of distributions are easy and which ones are hard, which kind of tracks pretty well what's happening for optimization. So the dichotomy is basically whether the distribution is log-concave, or in other words, whether f is convex and whether it's not log-concave. So when we're looking at log-concave functions, there's a bunch of provable algorithms, and in particular the one that I'm going to be talking about. But we sort of don't like it in practice because it's pretty restrictive from the point of view of modeling. So in particular, you can kind of think of these as sort of, just by virtue of the fact that convex functions have one sort of like minimum, they kind of look unimodal like that. And the types of things that maybe we want to sample from in practice would be sort of things that have multiple kind of crazy looking peaks like that, so something that's much richer than that. But of course, life is hard, right? So the same way that we can't optimize arbitrary functions, we can't sample from arbitrary distributions. So this particular setup, when you just drop all of the assumptions, ends up being sharply hard. And this is, as I said again, like paralleling what's happening in optimization. So if you want to minimize a convex function, that's easy. Local minima are global, so you're fine. Same thing here, basically. Like you can just run Langevin diffusion. If the distribution is log-concave, it's going to be fine. Otherwise, life is hard. OK. So let me say a couple of words about prior work. There's, in some sense, sort of results here that are very, very classical. So they go all the way back to the 80s and sort of relate to some classic things in mathematics like Poincare and log-Sobolev inequalities. And basically, they say, in not so many words, that if f is convex, then reaching equilibrium is fast. And this could be like, either Pauli in dimension, or if it's a strongly convex f, then even dimension independent things. And then there is kind of a resurgence of interest in analyzing these diffusion processes, in particular their discretized form, which basically started with a paper by diparoux in 2016 and sort of kept going from then. And in some sense, what a lot of these works were kind of concerned with is proving that you can pick a discretization such that, in some sense, this discretization tracks the continuous process pretty well, and the amount of steps that you need to run it for is basically comparable to the amount of time that you need to run the continuous process for. And what's sort of the downside with this is, obviously, if you have a case where the continuous dynamics are slow, then who cares that the discrete ones track the continuous ones, right? So in these particular cases, it's of no help. And in some sense, sort of I guess the thing that we want to understand first, or like the thing that's to be understood, is how the continuous process behaves, because most of the time these tools kind of show us that we can basically pick a discretization such that we don't suffer too much. More or less, we have to run as much as the continuous process. OK. So then the question we sort of... Whoop. Sorry. All right. That is Andrej from the past, not from the future. It would be good if it was from the future. Right. So the thing that we want to, I guess, answer is much in the way that we've been trying to go beyond convexity for optimization. We kind of want to poke around and we want to figure out what kinds of assumptions can we make on the distribution that go beyond log-concavity and in which we can still give some provable guarantees. So I sort of originally got interested in this about a year and a half ago. So let me just show you something simple that we proved at that point, just to kind of motivate what I'm going to be talking about, sort of the new thing that we're going to be talking about. So the easiest thing you could imagine that's not log-concave, but kind of is something that you might want to look at in practice, is something that's multimodal, but it's kind of multimodal in not too crazy of a way, right? So you could imagine that your distribution looks like a mixture of shifts of some fixed log-concave distribution, and what this is sort of going to look like is something like what I have down below here. So it's something that kind of looks like it has n modes, so however many components you have, and the modes sort of look similar to each other because they're shifts of the same distribution. And then what we showed in this work was that if you basically run Langevin dynamics along with some heuristic, which is kind of like a temperature changing heuristic called simulated tempering, then you can basically sample from distributions of this type in time that runs polynomial in the number of components, so that's the number of modes, and the ambient dimensions. And so one kind of reason why I'm showing you this is there's a sense in which this is capturing something that people care about in practice, and there's a sense in which it's lacking something else, right? So what it is capturing is the fact that You want to do something that's multimodal, so okay, like this is probably the simplest multimodal thing that you can imagine. However, if you think about what the modes of this distribution look like, they're point masses, right? Like, so there are these little peaks here. And if you imagine what might be happening in practice, it will be typically the case just by virtue of the fact that it's sort of typical to train these very, very big models that have a lot of invariances, that your basically distribution will have sort of manifolds along which the value of the probability distribution is constant. And so sort of you want to be able to at least say something about what, like how the geometry of these manifolds of invariances affects the convergence time. And of course, this is kind of also useful on its own because maybe sort of you have a model and you're not exactly sure what kind, like what kinds of sort of transformation it's invariant to. So maybe you want to do something exploratory and you want to sort of figure out which points are getting treated equally by your model. Okay, so this is sort of the so sort of invariances and manifolds are the type of thing that I want to focus on. So what is sort of the simplest case you might imagine where we might be able to say something provable? Well, it's basically this entire class of matrix factorization style objectives, right? So suppose that I look at a distribution which is defined over, let's say, matrices of size d by k, and the objective, sort of the distribution has the form that p of x is proportional to e to the minus some scaling factor times xx transpose minus m for Frobenius norm squared, and let's say just to make life as easy as possible, this m is some d by d matrix of rank k. So what are the kind of invariances that this distribution captures? Well, it's invariant under orthogonal transformations, right? So if I take p of x and if I take p of x times r for any orthogonal r, the value of p doesn't change. It's a kind of invariance. So what am I expecting to happen for very large beta? So for very large beta, we expect that this distribution is going to concentrate basically like over the two. It turns out there are two sort of manifolds of, I guess, like of optima, which are not only disconnected, but they're also kind of separated in space. So one of these manifolds is you basically pick any fixed optimum, let's say x0, and then you multiply by a matrix in the R in the special orthogonal group. So this would be an orthogonal matrix that has determinant +1, or you can multiply it by an orthogonal matrix that has determinant -1. So this is kind of my skills of drawing things in 2D eventually break down. So this is sort of like a very, very cartoon version of what this might look like. But we should keep in mind is two manifolds that have some separation between them in Euclidean space, and sort of the distribution concentrates near these two manifolds. Are there any questions about the qualitative picture? Okay. Cool. So let's kind of explore qualitatively what we can hope to do here. So I'm sort of keeping up the distribution that we're sampling, that we're trying to sample from, and I'm also sort of reminding you what the chain that what the Markov chain we're looking at looks like. So basically, okay, I guess I'm sort of cheating a little bit in the sense that what I showed you before is that you're taking like gradients of the function and you're injecting Brownian motion, and I sort of put the scaling here from the temperature into the Brownian motion. You can just believe me that this doesn't matter basically. Like you can put the scaling of beta into the function, or you can put it into the Brownian motion. It's the same stationary distribution at the end. So what can we sort of hope for here? Like what should qualitatively the picture be of what this process behaves like? Well, imagine that you started with some point x0, which is maybe at this arrow that I started drawing things from here. And imagine that beta is large. So what should be happening is that this gradient term is basically providing you with a drift, which is kind of pushing you towards the closer manifold. So if I started closer to E1, it's going to kind of keep pushing me towards E1. And this Brownian part is kind of like, sort of like isotropic noise. So it's kind of pushing me around this manifold. And I should say that this sort of the gradient kind of pushing you towards the manifold is a consequence of this objective being locally convex, basically. And these are the types of things that people have looked at when analyzing sort of these kinds of objectives from the point of view of optimization. And then what we can hope for is that if I sort of have a beta which is large enough, and I sort of wait for some sufficiently long time, the time to escape from this, like from being like in the attractor zone of one of these manifold and get to the other one, is long enough that I can basically hope to mix to the distribution that's basically p, but sort of rescaled so that it's restricted to the neighborhood of the manifold that I started closer to. Okay, so my hope is basically that qualitatively that maybe I can sort of mix to the kind of conditional distribution restricted to being closer to the manifold that I started closer to in the beginning. Questions? Yep.
Are you relying on some meta stability with that?
Implicitly, right? I mean, like that's more or less one.
You need some separation.
There is separation. There is separation. Yeah. I mean, like the yeah. Okay. So if the qualitative picture is clear, let me sort of like state some simple version of the result. There's kind of more complicated version, but let me state a simple version of the result. So suppose that I take the temperature to be large enough, right? Like, so suppose that I take this beta to be large but finite, so maybe polynomial in the dimension, and for starters you can basically ignore this delta parameter. And let me call pi of x this distribution, which is basically the rescaled distribution of p subject to the point basically being closer to one of the manifolds rather than the other, right? Like, so this is just saying if I look at the point x, its projection to manifold EI is closer than to the manifold 2 minus EI. And otherwise it's 0. And so suppose that I start with some point which is sufficiently close to EI. So sufficiently close here will mean basically something like sigma min over k, where sigma min is the smaller singular value of m. And I run for some number of steps, let's say for number of steps t. Then what's going to happen is I'm going to start getting closer and closer to the distribution pi and in some measure of distance. So the particular measure of distance that ends up being easiest to handle is chi squared. So if I look at the distance between the distribution pt, so that's the distribution of the tth iterate of my Langevin diffusion. In chi-squared distance from pi, it'll be basically like at most some fudge factor delta, which you can ignore for now. But basically the important thing is that it drops off like e to the minus t divided by something, and this something is basically something that depends like on the rank of the matrix M and the temperature beta that we're looking at. So in other words, what this is saying is that if I basically think of beta as, let's say, sort of going into beta being something like t being something like poly in D or something, I'm going to start getting closer and closer to pi, but sort of it's not enough time for me to bump myself out of the manifold E1 and start getting closer to E2. Questions about the statement? This is in the infinitesimal case. I'm going to say a word, but it doesn't. Yeah, I mean, like all of the discretization stuff just basically goes through immediately. Like there's no work there. Okay. So what are some? Yep.
Same kind of way.
Yep. Same thing. Yeah. The time that you would sort of the discretization is such that the amount of steps you need to run it from is basically something like that. Yeah. Okay. So. So the delta there that I'm parameterizing is because I'm trying to sample from the sort of distribution that you are restricting to being closer to E1 rather than E2. So there's some probability that you're going to get bumped out, basically. So think of this delta as maybe something like polynomial in D or something. There's an exponentially low probability that your like chain is going to drift and go to E2. So that's why there's like this delta. So, like imagine having two chains, and one of the chain is sort of restricted never to leave like the neighborhood of E1. The other one can, in principle, leave it, and you're trying to basically figure out like what's the probability that the two like split apart at some point, and that's exactly that delta factor. Like that's the probability that you sort of drift from being closer to E1 to being closer to E2.
But this is in one step. Like how is that not depending?
No, you can bound like the probability that if you run for t steps, what's the probability that at any one of like any time between 0 and t, you left like if you started closer to E1 than E2, what's the probability that you're going to get closer to E2 at some point between 0 and t? Yeah. Cool. Okay. So this is kind of the cleanest version. There's sort of some natural extensions of this you can do, which maybe you can kind of intuit already. So you can basically sample from things that look like p of x is proportional to e to the minus beta f of x, where, for instance, you can take f to be the loss, sort of one of the typical losses that correspond to things like matrix completion and matrix sensing. So in particular, you can take f of x to be some linear measurement matrix, a linear measurement vector of xx transpose minus b, where this linear operator is collecting the measurements, which are either projections or some basically measurements that sort of satisfy the usual assumptions to prove that what you kind of make when you're trying to study the problem from an optimization point of view, which in the case of matrix sensing would be something like restricted isometry. In the case of matrix completion, it will be something like incoherence. You can have basically like the sort of statistically meaningful, I guess, version of this, where you sort of have a Gaussian noise version of the above. And what I mean by that is the way that you're getting these B's is by injecting sort of Gaussian noise with basically like scale with the appropriate scaling, such that this P of x that we're sampling from is basically the posterior distribution over x in this model. And as Philippe asked, like the discretization here is fairly standard, so everything that I said you can also sort of you can also do it for the discrete version of the chain. There's nothing kind of complicated going on there. Questions? Sorry? Huh? All right. So let me basically tell you some I guess like bits of the analysis and what goes into the proof. So one of the I guess basic tools that we're using is Poincare log-Sobolev inequalities. So these you can kind of think of analogues of spectral gaps that for the discrete version of Markov chains. So they're kind of some notion of spectral gaps for some kind of analog of a transition operator for a diffusion process. And then we also sort of use some results which basically say that log-concave distributions, I guess I kind of mentioned this, log-concave distributions have good Poincare inequalities. And we're also going to leverage some connections between the geometry of the manifold and the mixing time of a Brownian motion of that manifold. So these are sort of also like things that I guess like have been studied in math. And I guess in particular, just so I put something for you here. For instance, if you have a distribution P that has a Poincare constant which is bounded by C, then like a consequence of this is that you can get fast convergence for in chi-squared distance with something that looks suspiciously what I had on the previous slide. Like, so if the chi-squared distance drops off exponentially quickly, where the sort of factor by which you're dividing is the Poincare constant.
Maybe something. Are you
not
strongly log-concave here in this setup?
What is strongly log-concave?
Well, I mean, don't you get the right? So here, the Poincare inequality. I mean, if you could go with the KL, right? If you had a log-Sobolev inequality.
Yes.
Yes. And you don't have a log-Sobolev inequality for this problem.
It's a bit complicated. Yeah, I mean, like I have Poincare inequalities. I don't have log-Sobolev inequalities, but also like there's like a decomposition theorem that you're going to see like in a bit, which doesn't work that well with KL with sort of convergence in KL, but it works very well with like Poincare inequalities. So. There are bits of the proof that I don't know how to do in KL. Like, let me put it that way. Yeah. Yeah. And so the other kind of thing that we're going to use is some form of decomposition in sort of theorems, which sort of roughly you can think of as if you have some distribution which is defined over two sets of variables, let's call them S1 and S2, to get a Poincare inequality for this distribution, it sort of suffices to a first order approximation to get a Poincare inequality for the marginal distribution over the S1s, as well as for each of the conditional distributions S2 once I fix the values of these S1s to be something. And for us, this is kind of only like a first order approximation in the sense that there's going to be some complications because we're working with manifolds, so there's going to be some measure theoretic basically complications. Our distributions are going to be defined over manifolds that have some codimension which is bigger than 1, and so we're going to have to use some measure theoretic tools to make this work. In particular, we use something called the co-area formula. Okay, so let me sort of press on. So let me start with something which is like a minimal desideratum, right? Like, so what's at the like sort of very minimum that you have to have satisfied, at least for the set of minima for you to be able to get anything more or less. So if I think of the limit of what's happening when I let beta go to infinity, I'm basically more or less doing Brownian motion on one of my manifolds, right? And so at least in that case, what you want to sort of ask is, what is a class of manifolds, or maybe another way put, like what kind of geometric considerations do I have to have on my manifold in order for Brownian motion to mix fast? And it turns out the geometric quantity here that's relevant is something called the Ricci curvature. So a manifold that has a positive Ricci curvature, you can kind of think of it sort of as a round sphere, basically. And I'm not going to define it, but I'm going to at least intuitively tell you what it captures by drawing a bunch of pictures. So what it captures is effectively the following. If I take some subset S, maybe like you think of it as a bunny on my manifold, and I think of how the volume of this set evolves as I basically swipe the points in the set according to the parallel transport in some direction V on the manifold, right? Like, so you can imagine, I haven't defined parallel transport, but you can imagine like what would be happening on a sphere, right? Like you take a vector and you sort of try to transport it at different points on the sphere, so something like this, and then you sort of try to move each of the points on the set a little bit in that direction. And so what the Ricci curvature is measuring is how this volume changes, and in particular, if you have a manifold that has positive Ricci curvature, then this volume is going to sort of like shrink faster than it does, at least as fast as it does on a sphere. And if you have a manifold with negative Ricci curvature, then it kind of expands, so it kind of looks hyperbolic rather than spherical, basically. So, so that's sort of on a very high level what Ricci curvature is capturing for you. And the reason why this has something to do with mixing time of Brownian motion, again, you can sort of be very high level, but basically the intuition here comes from kind of trying to imitate the proof for coupling two Brownian motions in flat space. So there's this famous coupling if you have two Brownian motions in Euclidean space that which basically says you couple the two Brownian motions by basically reflecting around the hyperplane which separates them. And the nice property of this coupling is that if you look at the difference between the two Brownian motions xt and yt, it itself is a Brownian motion. And if you try to imitate this proof on a manifold which is not flat but has some curvature, in particular if it has positive curvature, then sort of the contraction is only increased basically. And so you can imagine that if on a plane this coupling is giving you something which kind of behaves like white noise, like Brownian motion, if you have something that has some non-trivial curvature, you basically get some white noise and some contraction. And this is sort of the idea for why Ricci curvature is helping you with mixing times of Brownian motions. Okay. And so now, okay, so this is a minimal desideratum because this is kind of only thinking about what's happening when beta is large, but it's finite. Sorry, when beta is going to infinity. Of course, when beta is large but finite, what's going to happen is that we'll be close to one of these manifolds, but not actually on it, right? Like, so we have to figure out how we're going to deal with not actually sticking to the manifold, but being sort of just nearby it. Okay, so let me tell you what's the high-level strategy. And the way that I'm going to explain the high-level strategy is by looking at a much simplified case, which nevertheless captures most of the ideas. So the simplified case is where I'm going to think of my manifold of optima as just being a circle. So it's a circle that's embedded in 3D. So it just looks like x squared plus y squared is equal to 1. And z is equal to 0, and I'm going to think of my distribution that I'm trying to sample from as just being p of x is proportional to e to the minus some scaling factor times the distance of the point from the manifold, which is here the circle. And in particular, I guess if you want to sort of imagine what this distribution looks like, the level sets of this distribution kind of look like toruses, or tori, sorry. Okay, so the strategy that we're going to employ is the following. It's kind of going to be a conductance argument. So we sort of wonder what are any potential bottlenecks, so if any, right? Like, or I guess ideally what we want to show is that there aren't any bottlenecks for this Markov chain. And the strategies will be to kind of foliate our space into things which are translates or scalings of our set of optima. So in this particular case of the circles. So intuitively, what this is going to get us is the following. So we're going to think that there are basically two sort of corner cases or two extreme cases that we want to consider. So one is that if I sort of am looking at sets which are entirely contained inside one of these elements of the foliation, they expand well. And the other sort of extreme are sets which kind of almost entirely cut across elements of the foliation. So if you want to think of that picture, like I want to say that there are no bottlenecks which are kind of completely aligned with these circles, and there aren't any bottlenecks if I think of something that kind of almost entirely just crosses these elements of the foliation. And so how do we do this? So let's take any arbitrary point on the manifold E. So let me take the point 1, 0, 0, let's say. It doesn't take too long to sort of write down the normal space. So the normal space is basically the space which is orthogonal to the tangent space at that point. So it basically looks like things which are as follows. So it's basically like S times some vector which has coordinates cosine of v, 0, and sine of v. And this S is going to like run basically between 0 and some nearby distance which we're sort of committing to. And so now what I'm going to do is I'm going to map this normal vector to a normal vector at any other point on the circle. So I can parameterize any other point on the circle as cosine u, sine u, 0. And the way I'm going to do it is pretty natural. So I'm going to map the point s cosine v, 0, and sine v to the point s cosine v, cosine u, cosine v, sine u, and sine v. So this gives me basically a way to take any normal vector in the normal space at x0 and map it to a normal vector at any other point on E. And now here's how I form the translates. I'm basically going to take any point on E, and I'm going to add I'm going to add the normal vector at that appropriate point, like according to this transport map. So if I just write it out, it just looks like the point on E, which is cosine u, sine u, and 0, and then I'm adding plus basically like the translate of that normal at that point. And if I write it out, like it exactly looks like these circles that I have on the on the image there, right? So what I did is I basically took all of the entire space that's close to my manifold, and I basically partitioned it into these sort of little circles, which I get to think of as sort of translator scalings of the manifold E. Okay, so now what is this decomposition theorem that captures, I guess, this intuition that there are no bottlenecks in this for this chain? So it basically says the following. So it says that it suffices to show that if I look at the distribution of the level sets, they have a good Poincare constant. And the way that I'm going to sort of argue that is that I'm going to effectively say that this distribution is something that's approximately log-concave. And also, if I look at any level set, the distribution restricted to that level set has a good Poincare constant. But this I will kind of almost get for free, right? Because I set things up so that the translates are so that these are like translates of E, and E already has E is a circle, so circle has a positive Ricci curvature, so I kind of almost get that for free. So here's a statement of the decomposition theorem. So it's pretty natural. So I'm going to denote this map F, which goes from 3D space to 2D space, which basically maps a point X to the appropriate sort of a member of my foliation. So the members of the foliation are indexed by S and V. So the map goes from X to S comma V. And then I'm going to just introduce some notation. So I'm going to say that if I look at any of these members of the foliation, so let me call them M, S comma V, which as before, like I said, I guess they have these forms. And then I'm going to also denote the distribution P over this manifold to be the following one. So it's essentially like the original distribution that we're trying to sample from, restricted to this manifold. But it has a small correction factors, and the correction factor is basically something that's kind of like a change of variables formula, and this comes from this co-area formula from measure theory. And what I'm denoting here, which you don't have to worry too much about, is this is the bar above denotes that this is the normal Jacobian rather than the regular Jacobian. What this means is you take the Jacobian of the map F, which goes from RT to R2, so that's going to be like a 3x2 matrix, and you just look at the basically like 2x2, I guess, invertible linear map that you get from that, and you look at the determinant of that map rather than the entire matrix. And then what's Q? So Q is basically the distribution of these members in the foliation. So you just look at basically the distribution that you get by sort of integrating of the probability mass over that particular member of my foliation. So this is pretty natural, right? So what you should think of if P of S comma V is kind of like the restriction of the distribution we're trying to sample from over this one of these members in the foliation M comma SV, and then Q of SV is sort of the conditional distribution of the members of the foliation. And so then the decomposition theorem says that if the distribution P has some Poincare constant, let's call it C along, and this Q has some Poincare constant C across, then the Poincare constant of the entire distribution is no more than the product of the two things. Another way to say this is that if I have a good mixing time for this distribution and a good mixing time for this distribution, then I get a good mixing time for the entire distribution of my interest. So that's the sense in which this is a decomposition theorem. Questions? Okay.
Yeah. So the Ricci curvature gives you the Poincare constant.
Yeah. So I guess maybe that was going to be my next thing, right? Like, so if I look at P of S comma V, because I took these things to be level sets, P S comma V is essentially a uniform distribution over the circle. A uniform distribution over the circle has a good Poincare constant because the circle has positive Ricci curvature. So that's why I basically that's why this guy has a good Poincare constant. And then this guy, once you do a little bit of simple math, again, because of the fact that these are sort of, I took the members to be basically level sets, you can sort of just do some very simple math and see that this Q of S comma V is something that's proportional to basically e to the minus s squared. This is a log-concave distribution. So that's why that guy has a good Poincare constant. So both of them have a good Poincare constant, so you put them together. Other questions?
So in the general case,
yeah.
Here you mentioned the circle, but I guess in the general case.
So I'll say like like 1.5 slide basically. If you're going to ask like how do we get, maybe finish your question because I'm not maybe.
I was going to ask
yeah.
What is the Ricci curvature of the level sets?
Yes,
that you need?
I was going to have like one slide on that, but okay. Yeah. So maybe I'm finishing at 3:30, right?
Yeah, but you started maybe 2 more minutes. You can take an extra 2 or 3.
Sure. It's anyways. I'm like very close to done. Okay, let me just say a few words for Philippe, right? Like, and so let me skip the slide, right? So, yeah. So how do we argue about the curvature of the of the set of optima for our case? So what we end up leveraging here is the fact that we have some algebraic structure. So in particular, there's basically maybe let me do it like this. So.
2 more than the 2 I offered you, if it helps.
Oh, that's well. Don't give me extra time. Yeah, that's too mean. Yeah. No. Okay. So maybe let me just do this slide a bit slower, right? Like so there's this. So what we're leveraging is that there's some algebraic structure to our sets. So in particular, if you recall, like a Lie group is basically a group that has both manifold and differentiable, both manifold and group structure. And what that means is that if you look at basically A composed with the inverse of B, where the composition is according to the group, that's differentiable. What you sort of know is that if we look at our particular set of optima, which have the form x0 times u for some u, let's say in the special orthogonal group, they have a Lie group structure by just basically copying the group structure from the special orthogonal group. And then there's a theorem due to Milner, which basically says that if I look at a Lie group and I equip it with something with something called the left invariant metric, which is pretty natural, it just basically says like the metric basically should be preserved under translations by any group element, more or less defined in some appropriate way. So if I equip a Lie group with a metric of that type, then I get a manifold that has a positive Ricci curvature. So there's an additional complication for us because sort of the natural group operation that gives rise to like a natural left invariant metric is not the Euclidean metric. But basically what we can say is that if you sort of equip it with a natural metric, then you can sort of massage it enough to be able to say that there's also like you can relate the Ricci curvature with the group metric to the Ricci curvature with the Euclidean metric by losing something basically. And that's how we argue that the manifold of the 2 manifolds of optima have positive Ricci curvature. So that takes care of it.
You need to actually have a control in terms of like, what if it's exponentially small in the dimension, for example, the Ricci curvature?
It's not, right? Like so if you have the Ricci curvature of SOK is like lower bounded by k basically. Okay. And now we don't have SOK, we have something which is like a linear transformation of SOK by multiplying with some matrix, whatever, like x0 here. So you lose something like the sigma min or something like of the matrix x0, you can relate it in some particular way. Yeah. And okay, so basically then the strategy is more or less the same one as before. I won't say much, but basically like it's kind of similar to before. You figure out how to foliate your space into things which are kind of like copies of SOK in this particular case. And you do the same thing that we did in the circle with a little bit more complication, but basically it's the same thing. So okay, to wrap up, I guess like there are some very natural problems that are open here that I don't have good sort of answers for. So in particular, even simple like latent variable models, which I opened with and I kind of never got back to, like sort of mixture distributions, like Boltzmann machines, VAEs, like sampling posteriors, even in very simple cases, is pretty tough and wide open. Diagnosing convergence of sampling algorithms is also a very big thing, in the sense that when people sort of run these things in practice, typically they have a bunch of kind of auto-regressive heuristics that they use, but none of them come with any provable guarantees. In fact, like if you just commit to worst case things, to sort of worst case guarantees, there's lower bounds that you can't really do anything there, but maybe we can do something if we make enough assumptions. And is there some kind of like sort of implication that we can get from sort of analyzing Langevin dynamics for understanding how SGD behaves with models that are very overparameterized, if we maybe have some geometric understanding of the set of minima that it keeps close to. So let me stop there, basically.